You may know Auburn, but do you really know Auburn? We work hard, dream big, and soar past today's limits to the possibilities of tomorrow. Auburn, if you thought you knew us, think again. War Eagle.
Hello, my name is Grant Romine, and I am a PhD student at Auburn University, and today I will be presenting a framework for integrating Gurobi within Simio. Before we begin, one note, in this presentation, we will be using an example that will facilitate the explanation of the integration of Gurobi within Simio. So this example is trivial because we want to focus on the integration in this presentation. What do we mean by decision-making in discrete event simulation? In these models, decisions are made during runtime according to rule sets and logic that was predetermined and designed before the run. However, there are many real-world systems that have critical decisions that need to be made but are difficult to model using predetermined methods and may require scenario-specific decision-making. For example, when uncertainty in a model exists with future values, for example, unknown demand in a supply chain, deciding ahead of time could lead to poor decision-making. Decision-making is then reduced to locally best decisions that are myopic when we take the entire system into account. The purpose of integrating an optimization solver within the run of a discrete event simulation model is to reduce these myopic decisions. The result retains simulation's ability to deal with uncertainty and complexity while using optimization's global decision-making that takes into account an entire system. The framework being presented today uses Simio as the simulation software and Gurobi as the optimization solver. But it also requires the use of a SQL Server database and Python for scripting. Since there is no direct integration of Gurobi within Simio, the database facilitates the communication of data between these two pieces of software. Python is then required to retrieve data from the database and execute the Gurobi solver, and then return the results back to the database. It should be noted that this approach is different from input parameter optimization methods such as OptQuest, as we are using optimization to regularly make decisions during the runtime of a Simio model. In this presentation, we are going to use a motivating example to demonstrate each piece of this framework. The example chosen concerns order fulfillment. Now, this is a difficult and important problem, but for today's presentation, I have greatly simplified it for the presentation in such a way that it will put focus on the integration technique. And so we will not be looking at the best way to optimize to solve this problem or the results of a case study. So in this example, a company must fulfill a set of orders using its set of factories. Each period, it must decide which orders should be fulfilled and which factory should be assigned to each order. So I have listed here a few of the many possible options for predetermined rules. For example, the company could assign the orders to the factory with the largest inventory, or they could assign the orders to the factory that's closest to each customer. Or the company could use production information such as shortest production time or largest production capacity when assigning orders to factories. And of course, the company could also use a multiple criteria as well. In this simple example, you can see the sets of factories and sets of orders have been visually represented by the network on the right. The values on the factory nodes represent the current inventory at each factory, and the values on the order nodes represent the quantity of each order. The weights of each link are contained in the distance matrix you see in the bottom left. When applying one of the rules from the previous slides, we will work sequentially starting with order 1, then order 2, and then order 3. If orders are assigned to factories with the largest inventory, it's shown that order 3 cannot be fulfilled. Likewise, if orders are instead assigned to the closest factory to each order, again, order 3 cannot be fulfilled. A solution can be easily found to this problem, however, because the order demand is equal to the supply. And so what is shown here is that even when the demand and supply are equal, it is possible that a single wrong decision could result in poor decision making and in an infeasible solution. Now, I want to reiterate that we would not use this approach to solve this problem because it can easily be solved with a dispatching approach, even if the dispatching approach is not the one that was demonstrated. And furthermore, the optimization would easily solve this problem because it is trivial. But it is difficult in normal circumstances to find a set of dispatching rules that would be sufficient in every circumstance that could occur during a simulation's runtime. Before we walk through the specifics of applying the framework to the order fulfillment example, let's run through an overview of the interactions between each piece of software. In Simio, this framework is executed using a process. The main steps necessary to integrate Gurobi solver within a Simio model are a DB write step, a call Python step, and a DB read step. So because this framework is executed via a process, it can be applied to both periodic decisions and decisions that are triggered by events during runtime. During the DB write step, Simio writes current model data to the SQL Server database. With the call Python step, Simio will execute the Python script. Note that the call Python step is user-defined. The Python script then completes the following steps. First, it retrieves data from the database. Then that data is manipulated into data structures that will be then solved using the Gurobi Pi package. The results are interpreted, manipulated, and loaded back into the database. Then, during the DB read step, Simio will retrieve the updated data in the database and update its data table accordingly. The simulation model will continue until the next time the process is triggered and executed. Let's apply that generic process to the example of order fulfillment from earlier in the presentation. You may notice that the process in the top left corner has been complicated by the addition of 2 new search steps. In our order fulfillment example, our main decision was assigning each order to a single factory. To approach this problem, we will be dealing with a data table called orders, where we want to decide which value should be placed in the order location column. Furthermore, if an order is determined to be filled, the planned ship date column will be set to the date time value of time now. So the result is we will assign an order to a factory, and if that order is assigned to that factory, it will be determined to be shipped at the time of the process being executed in the simulation run. This process will trigger periodically intermodel whenever this decision of order fulfillment needs to be made. During the first search step, all unfilled orders in the orders table will be found via the properties of match condition and limit. So by setting the match condition to the filled column in the orders table being false, all orders in the orders table that have yet to be fulfilled will be found using this search step. The token wait action is also very important with this step, as all information needs to be written to the SQL Server database before Python is executed. So the tokens that are created by the search step and flow out of the found branch will have references to rows in the orders table. For each of these tokens, the DB write step writes one new record to the SQL Server database table that is specified in the table name property of the step. So for this example, in the SQL Server database, a table by the name of open orders is used. The DB write step also requires a DB connect element that is defined in the definitions tab of the model and listed here. This is important in order to connect the SQL Server database and the Simio model. The columns repeat group of the open or of the DB write step creates a mapping of the data in the Simio data table and the data in the SQL Server database table. The value placed in the column property refers to the column in the SQL Server database table, while the expression refers to the piece of data from Simio that will be placed into SQL Server. One thing you may notice is that some care is necessary in order to write the correct object names or date time values to the database table. Next, the call Python step requires two arguments. The Python executable location property requires the path to the Python executable on the machine that is running the Simio model. And the Python script path requires the name of the script Simio should execute during the call Python step. The path for the script can be absolute or it can be relative, as Simio will search the same directory where the model is saved. For this example, Python must retrieve data regarding three different aspects of the model. First, current inventory position data is pulled from the inventories table. Second, transportation distance data is pulled from a transportation lanes table that details the connections between nodes in the supply chain. And lastly, Python must retrieve the unfilled orders data that was just updated by Simio in the DB write step. Now, I haven't mentioned the inventories or the transportation lanes tables for brevity in the presentation because most of the data in both these two tables is static during the runtime of the model and simply defines locations and connections. For this example, let's look at the optimization model that is going to be used when making this decision of assigning orders to factories. For this example, the objective function is to maximize the difference between the reward for fulfilling an order and the transportation cost for a factory to fulfill a specific order. So the binary decision variable xij is 1 if factory I is assigned to fulfill order j and 0 otherwise. The first constraint in the model constrains the demand that is to be fulfilled from not exceeding the supply at any single factory. And the second constraint allows an order to be unfulfilled, since the model would be infeasible if total demand exceeded total supply. It should be noted that reward for this simple model can just be set to a single value, but in more complex models could stand for orders that are needing to be fulfilled earlier than others, orders of higher quantities, and so many different methods for determining what a reward is could be considered for this optimization model. Now back in the Python script, Python retrieves the data from the database. It will then manipulate the data that it retrieved from the database and construct data structures that represent that optimization model for Gurobi Pi. One of the powerful things here is that no matter the number of factories, the number of orders, or any current inventory levels, Python will always construct a appropriate optimization model for the current situation in the simulation model. Python interprets the results that Gurobi returns after solving the optimization model and updates the origin location column in the open orders table of the database for each order that was assigned to a factory. It also assigns a planned ship date value of time now to each order that was assigned to a factory. Once the Python script has been executed via the call Python step, Simio must retrieve the new data from the SQL Server database and update the orders data table. This second search step is identical to the first search step because Simio needs to check whether updates exist for each unfilled order. For each token that flows out of this second search step, out the found branch, the DB read step executes a query to the database. So a query is executed for each unfilled order record in the orders table. The results of the query are then read into a Simio variable. Here, the data from the open orders table in the database will be directly placed into the orders table in Simio. Again, in the DB read step, much like the DB write step, the DB connect element is necessary. Here, the columns repeat group also creates a mapping between the data in the SQL Server database, which is noted by the column property, and the Simio data table noted by the state property. So you can see here that we want to map the data from the origin location column in the database to the orders.order location column in the Simio data table. And likewise with the planned ship date. The where repeat group defines the where statement in the query by equating the value in the where column property and the where state property. So for this example, the records in the open orders table in the SQL Server database and the orders table in Simio are matched using the order number value because it is a unique value for each order. So for each token that comes out of the search step, a query is executed, and for each order, the values in the origin location and planned ship date columns of the Simio data table are updated if updated data exists in the database table. The result of this process is an orders table with values in the origin location and planned ship date columns. So for our example, the optimization model was able to find enough supply at the existing factories to fulfill all 6 orders, and thus also assigned a planned ship date to each of the orders of the 1st of January of 2021. Now that these decisions have been made, Simio can execute fulfilling these orders. So using an example of order fulfillment, I have demonstrated a framework for integrating Gurobi optimization within the runtime environment of a Simio simulation model. This was executed via a process and used a SQL Server database and Python programming to facilitate communication between the two pieces of software. In the example, making the decision of assigning orders to factories was made with all available system data, which resulted in a globally made decision that avoided being myopic. While this example was simplistic, the framework can easily be expanded to include more uncertainty and more complexity. And while this example was in the domain of supply chain management, this framework could be applied to areas of healthcare, manufacturing, or scheduling, amongst many others. If you found this presentation interesting, I would like to point you to 2 resources. The first one is a post over on the Simio forums titled Synchronizing a Simio Output Table with a Database Table that demonstrates another use of this integration, particularly Simio and SQL Server. The second resource is an installation document that we have created that details installing the software and then configuring each piece and the communications between them. If you are interested, we can share that with you. I hope that you have enjoyed this presentation, so thank you for attending.
Hi, Jeff. Hey, Grant.
Hey, Adam, how are you?
Doing well. Thank you. Grant, I wonder if it's possible to deactivate your webcam. It's strobing of sorts.
Well, so what's weird is I have it disabled and I see a GR and I don't see a strobing webcam on the stream.
Then no worries. We'll have an extra colorful final Q&A session here.
Yeah, I'm some
No worries.
80s TV or something.
Hey, really enjoyed the presentation, guys. And as a quick point, someone had asked about the call Python step, whether it was publicly available, but it sounds like right at the end, you opened the door for folks to reach out if they have questions about this. Is that correct?
It's also on the GitHub. It's on the Simio GitHub.
Excellent. Excellent. Okay. Great. So first question we have here, a bit more specifically, what benefits are there when using Gurobi integrated into Simio? So maybe just generally you could speak to that or explain through healthcare, manufacturing, another example you mentioned. Have you been able to use this in actual projects?
This is a good question. So we are currently experimenting using this integration within projects. But as far as the benefits to using a Gurobi optimization model would be to improve a So there's two types of decisions. One would be a periodic decision that's made in the model, and to make that decision using an optimization model instead of relying on a dispatching rule. And so you can know that the result of that decision is made using an optimization model. And then there's another option, which is using the optimization model to make a decision if an event is triggered, to assess the current state of the simulation and to make the best decision about going forward at some predetermined event that's triggered. So I would say those are two of the benefits. I don't know if Dr. Smith has another thing
No,
on
I think
top.
it's just what you said in the presentation, Grant, that it lets us make globally optimal decisions if for anything that we can formulate. So anything that we can formulate as a linear optimization or any kind of optimization that Gurobi can solve, we can solve that and then feed the information back into the model as it executes.
Very interesting and definitely related here. Someone has asked, how does using Gurobi or an optimizer compare to using the neural network feature within Simio that was presented earlier today?
So Grant, I'll take that one.
Okay.
So it's a similar process in that we are stopping the model, we're stopping simulation time, solving an optimization, and then writing the results back. And the neural network feature does a very similar thing. It's embedded inside the Simio, so there's no need to execute an external process. It just happens within Simio, but you are stopping simulation time and making some type of decision. So these are just two different optimization methods that are applied.
Perfect. I think that's a great breakdown, though, really, of sort of the workflow that's happening there. So thank you for that. And let's see, maybe we'll do one final question. Not to put you on the spot, maybe you know. Is there a way, have you explored doing something similar with other scripting languages like R, MATLAB, or anything else?
So Grant, I'll take that one also. Sorry. It would be the exact same. So whether you want R or MATLAB, we just use Python because we have Gurobi Pi and set up, and that's what we're used to using for formulation. But you could do the exact same thing with R or MATLAB using basically the same workflow, because the call Python step, while it's called call Python, all it actually does is calls an executable, which could be R, it could be MATLAB, in a separate run space.
That's great. Well, I think hopefully some light bulbs are going out for folks out there who are better programmers than me. So really enjoyed it, guys. Thank you so much for the time and your participation here.
Thanks, Adam.
Thank you.
Hi, guys. Be well. Thanks.
I hope you enjoyed all the presentations during this week's Simio Sync Practical Applications event. I would again like to thank everyone involved in the event and all of you for attending. We will be hosting our next Simio Sync event in the fall. Look for more details from us in May.